Hello, I'm Amit. I'm an senior data scientist at Intellicredence. I would like to tell you one story. It's a story of a project. The project basically belongs to one of my friends. She's from Maharashtra, Mumbai, and her vision, and her startup vision was to deploy medical AI in a region where there are no GPUs, no TPUs, no clouds, okay, and no reliable internet connection. So the overall project journey goes from deploying a big AI model onto an edge device. Okay. So what exactly is the problem? So as we know that India is a big marketplace for diabetes patients. Okay. So if the diabetes is not cured early, due to the diabetic retinopathy, the patient can lose their vision. Okay. So as you can see, they were having a model, Llama 3.2, 11 billion vision. Okay, so they were having a lot of data set they have collected earlier for to detect this retinopathy. Okay. And the major problem over here, as I've already told you earlier, that there were a lot of hardware requirement as well. The requirement was for a GPU NVIDIA A100. It costs around 850, 8.5 lakhs. Okay, but our target was to deploy it on a device that will cost around 15,000. Okay, so So, like they perform quantization over the model, and they perform INT4 quantization across all layers. Okay, but the accuracy decreased, and the predictions that were made over the LLM models were like completely not making any sense. Okay, so any guesses like how they solve this problem? Any one of you? Like after quantizing the model to INT4, if the model is not predicting that well, what all solutions she did at that time? Any guesses?
Inference.
No.
Another option would be patching it, and whenever internet gets available, it goes to the cloud.
No, there were no clouds, nothing.
Okay, prove out.
Yeah. Anyone else?
This distillation model technique works in this scenario?
No, like for now we have done just INT4 quantizations, that's it. Like to overcome the inaccuracy, what exactly she did, that I want you all to guess.
Floating point quantity.
Only few layers need to be quantized, not all layers.
No, actually after this, she called me. Okay. Yeah, correct. So, in the model, as you can see, the accuracy dropped from 89 to 71 accuracy in 94. Okay, created hallucination. It composed wrong text, and long tail issues were also there. So this is the model they used. Okay, over here we use mixed precision, the one you told. Okay, so here we are giving a separate importance to each and every layer. Okay, so as you can see, we are using the vision encoder layer on the top. From 0 to 8 they are convolutional, and the last one is the attention layer. Okay, and after this we are stacking it with the text transformer. Okay, for medical reasoning specifically. So from layer 0 to 8, we compress, like before, as you know that all the layers were compressed to INT4, it didn't predict it well. So what after this, she compressed layer 0 to 8, the convolutional layer were compressed in INT8 format. Okay, attention layers were compressed in MX6. So now what is MX6? Anyone? No one, guys? MX6 is nothing but it's INT6. Okay, it's alternative to INT6 where the values are stored not in form of a whole number but in form of decimals. Okay. So if layer is compressed in INT4, okay, the predictions can be only made in a form of a whole number, 0 or 1. Okay. It can't include the decimals. Okay. So after compressing of these layers, in text transformer first, it uses the pattern recognition, okay, from 0 to 15, from 16 to 21, it has the critical medical diagnosis happening here we did MX6, and from layer 22 to 28, was contest in INT4 again and language translation and code switching, okay. Layer 29 to 35, we had MX6 decision making, and layer 36 to 50, we have INT4 output formatting, and the last layer was the output head. That was also INT4, final prediction thing. So what went wrong? Okay, this was a old method, that is INT4, okay, that store only 16 possible values, okay, 2 to the power, okay, 2 to the power 4, okay. So the range of the values that are stored in INT4 is like from -1 to +7. So these are complete 16 sets of values, okay. So as you can see here, it cannot handle the decimals. So if the prediction is like something 0.375, it becomes 0. It won't take this 375. Okay. So here we opened the problem with this thing, the MX6. It's like it stores the 64 possible values. It's like INT6 2 to the power 4. Okay, no, not 2 to the power 4. Yeah, it's 2 to the power 6, sorry. So after we take out the value, it is somewhere like 64 possible values, okay, that are 4 times more than the existing method. Okay, it use a scale parameter and a Mantessa parameter. Anyone who knows what Mantessa is? How is Mantessa calculated?
Mantessa is what, the fractional value, is that what Mantessa?
I want a formula if possible, like how Mantessa
No,
is
first of all, what is Mantessa is what I'm trying to know. Mantessa is a fractional part of your whole number?
No.
Use ChatGPT, Google is allowed.
Yeah, use ChatGPT you can. But in terms of this, it will give something different. Okay, Mantessa is basically like if we have a set of numbers like 0.2, 0.6, 0.8, and the biggest number is 0.8. Okay, so dividing the number by 64, that is the scale value. Okay, and dividing that the maximum number with the scale value, we will get a Mantessa. Okay, so these parameters are used, and the scale value. If we want to store this number 0.375, it will store it as 0. But after multiplying it again with the scale value, the required value will be 0.375. Okay, the storage issue is also solved. And whenever the number is recovered, number is actually the weights in neural networks. Okay, whenever the weights are recovered, they are in the same form.
Tell me one thing. I think other layers outside are having integer, right? So when some layer has a floating point, some layer has only integers. So I think there will be some information loss.
Yeah, there is a little bit of information loss. This is not completely accurate. Okay, we'll lose some of the accuracy, like, but not much, like somewhere 2 to 3%. That's it. Okay, it won't be that precise, but we will be around the precision. Okay. So the problem was solved. Accuracy problem was solved using that method. The second problem that we came across was the KV cache thing, the memory thing. Like whenever we would be doing the inference, the model was getting crashed. Now, any idea why was the model exactly getting crashed?
Out of memory.
Yeah, out of memory. The model was getting out of memory. Can you tell me like what is a KV cache?
During inference, whatever the few KV computations happen. For that KV, I mean, it happens token by token. So for later parts, we actually want to reuse the previous inferred values. So we want to cache it, but ideally it's, but in basic setup it is not done. So we have to recompute the entire KV computations. So,
Right, you were close. Like
it's a kind of I'm not sure sequence sequence to sequence processing. It seems like so. It's next layer required our previous layers information. That's why we need to cache all those tokens of previous layer. Forward.
the language is auto-regressive, right? So after every token generation, it has to again go back to the whole cycle.
Exactly.
So in
So,
that, the computation, we want to reuse it.
yeah,
the
if you talk it in layman, so it is like a memory where the history is stored. LLM's history is stored. Like if you are using ChatGPT, it uses the previous history to predict the next thing. Okay, so the same thing is happening over KV cache is nothing but the key value cache where the history is stored in a form of key and value. Okay, so due to
Correct me. It is between layers or nodes when prediction happens. Those are the output taken of one node to another node.
No. In the transformer's attention, like each and every head has a separate cache.
Okay.
Correct. So each cache it takes some of the storage. Okay. So the same thing I would like to this is the solution, the group query attention. Okay. The group query attention is basically where all the heads in a transformer's attention are grouped. Like some of the heads are removed. For example, if I want to give you an example, if you want to teach 4 students in a class, allocating them four teachers. Okay. Obviously, they will perform pretty well in their semesters. But what if we allocate 2 teachers to 4 students? What do you think? What will be the results?
Still they can perform. Based on historical data.
No, there is no historical data. There's one class.
One teacher teaches 40 students.
Hmm.
Still, we are giving one teacher for 2 students.
Yeah, in conclusion, there is not a big loss. Okay, the same thing we are using over here. We are reducing the memory consumption by just grouping the heads into 4 instead of 8. Okay, they use the same memory. Okay, but the slots of memory are reduced. So this reduces the memory consumption, and hence we can overcome this crashing problem in an LLM. Okay, while deploying to an edge device.
So this 32, when you said that number, that is coming from 32 attention heads in the.
Yeah, 32 attention. So the third problem that we came across was the decimal point disasters. Like one day one patient came to the clinic. The doctors were the ones who were operating the device. The doctors asked the edge device like what exact dosage of anti-VEGF injections should be given to the patient. So the model predicted it as 1.5 mg, but the actual answer that needed to be predicted was 15 mg. So what according to you do you think what went wrong?
To take right decision.
Okay. Anything else, Ajit? Actually, in the earlier slides, we have seen that all the layers were compressed in 94. So the last layer, the output layer, was also compressed in 94 as well. Okay, so then it crossed the precision. So at the end, we compressed it to 98. Okay, and we kept a validation layer as well, where it checks the value is correct or not, whether the predicted thing is correct or not. Okay, so this was the thing at the last layer. Okay, this is we came across the 4th problem. Okay, the multilingual problem. As we know that a device was deployed in a rural area. Okay, where they speak the regional languages. So the model was not predicting based on the language it would given to it. Okay, like people were talking in, so this is mistaken, it was supposed to be Marathi. Okay, so if the people were speaking in Marathi plus English, it won't predict that well. So, what do you think what went wrong over here? I know from that side, I'm not getting any answers from that side. You can read the complete PPT. The answer is in that only.
So I think in Sentence, there are multilingual stuff. Basically for LLM, detecting would be a problem. If in a one sentence, if we are using only one language, that could be easier for them to. So for that, I think if we can translate in a one language, either in Tamil or English or Hindi, then we can pass through.
Actually, the model was earlierly trained on multilingual. So there is no need to translate.
With the loss, with this reduction in the number of maybe parameters or anything,
Yeah.
we lost the.
You must have noticed that all the problems are almost the same due to this layer compression thing. Okay, so the layer that was responsible to switch language from one language to another, that's a very delicate layer. It requires a separate semantic space in LLM. Okay, so due to compression of that layer in INT4, it lose the precision and it was not able to predict in different languages. Okay, so what we did. What must we have did at that moment?
Fine-tuned it with more data.
Yeah. We fine-tuned it with more data, and also from layer 22 to 28 was the layer that was responsible for switching the language. We quantized it to INT4 format again. Okay, and yeah, we have fine-tuned it on the multilingual thing also, the data. So the LLM problems were solved, and the final problem was the edge device. Okay, so whenever they used to do the inference, whenever they used to do the screening over patients, the device used to get heated up. Any idea? No idea.
So on the edge device only, the LLM was, I mean, what was the model that you were saying is was deployed on the same edge device?
Exactly. First, we used to quantize it on a correct machine, and then we used to deploy it.
So was it a LLM or a model is what I'm trying
It
to
was a LLM.
So LLM you ended up deploying on the edge device.
Yeah.
And the edge device has a GPU processing capability.
No. We quantized it. That's what I'm talking. We used llama.cpp.
So what was the machine under the hood on that edge device?
It was the Jetson Nano Orion.
And the processing power was?
I don't remember the processing power, but yeah, it was somewhere similar to Raspberry Pi 5. Yeah, 8 GB RAM. So, yeah, any answer for this? Yeah, you were raising your hand. That's all.
Keeping on my head.
Longer time for inferencing was taking longer time.
Yeah, that's what I'm asking, why it was taking longer time for inference.
I mean, you have not given it enough power and all, right? So obviously it is supposed to take.
No. Enough power was given to it. Okay.
I mean, in terms of, this infra is so limited. So obviously inferencing will take more time and the device likely power consumption will go high, right? So
Actually, due to the environmental conditions in Indian clinics, okay, basically usually the regional clinics, the rural areas, there are no air conditions, okay. So due to that environmental conditions, the edge device got heated up quickly.
So it's not a LLM problem, right?
No, it's not. I haven't mentioned any LLM problem over here. Okay, I haven't uttered a word.
So the solution was we needed more AC, right?
Well, my AC was in the rural area. It's not possible. So the solution we came up was like batching up patients. like putting patients into batch 4 by 4, taking a pause so that a machine can recover to a centralized temperature. Okay. So this made the project successful. Okay. This is a code snippet, okay, that I've used for quantizing the model. Actually, this will require a lot of environmental setup, okay. If possible, you can get a Docker image for it. Otherwise, you have to set up all the Python libraries with the suitable versions. Okay. We're done with taking pics. So,
Same right? Got a call from same guy?
no, I didn't got a call from this. So after the end product, the results were somewhere like this. The model size reduced from 44 GB to 4.5 GB. Okay, that was 11.5 times smaller than what it was. The inference time, the last inference time, I've not known about that thing, okay, because I entered the project a little bit late. When she called me, that time I entered. Okay. So the final inference time was, the last recorded one is 2.1 second. The accuracy is like 89%. It went from 89 to 86%, only 3% drop. Okay. And the cost was, as you can see, the cost of device is reduced from 8.5 to 4500. That's 48 times cheaper. Okay, so what happened in the real world was, like, the product was deployed to 47 health centers across Maharashtra, and 12,000 plus patient screening were completed using that device, and 18 early stage cases were detected and also treated. Okay. So these are the key takeaways that you should take out of this project. Okay. First is that not all layers are equal. We should not treat all layers the same. Okay. And we should not use any data that is available online that looks similar to what we need. We should use a real world data to calibrate, okay, while quantization. After that, the memory thing, it's not like if you have quantized the model, if you have compressed the model, it means that the model size is reduced. You should work on the KV cache as well, okay. You should work on the multi-head attentions to reduce the cache size. And the final is the environmental conditions if you're working on the edge device. Okay. Thank you. I would like to thank Ajit ji and Ramesh ji for inviting me over here. Thank you so much. Any questions?
What was the capability of that model? Like, what it used to do? Like, it was just a language model?
No. It was a multi-model, like text and vision. Like we saw, it's Llama 3.2 vision plus text.
Okay.
Yeah. So
What kind of queries would you put over there to get the answer?
similar to what a chat GPT or a cloud does, entering the image, if you're typing the prompt, that's it.
Okay.
Yeah.
Yeah, very specific problem. So I'm trying to understand whether such a small model was able to have that kind of variability in, or how much of variability was there or not there, and like so.
Actually, the PPT is very small, but it took a lot of time, okay, in the whole process. It's not like if we have used mixed precision, so it had worked. It was not at all the case. We have to work a lot on it, like what exactly went wrong in each layer we have to see, okay. So that's a very sensitive part over there in terms of data. So if you're giving a separate importance to each and every layer, it will obviously it will work.
How did you cut down the bias? Is there, because the model is so small, is there a probability of bias in it that it's going to work?
There was a little, yeah, because see, we came across the bias, but at the end we put a human validation after each and every prediction. We can completely rely on it. That's why. It's not like there were like 18 cases detected, early cases that were detected, but there were also some cases detected that were inaccurate. Okay, fixed, but I haven't added it over here because I don't want to fail my PPT. That's all.
How many images did you use? How many images did you use?
I don't have any idea. I was not there during the fine tuning.
And what is single size roughly?
Means you are talking about resolution.
Ah,
256 into 256. Yeah.
So it was kind of camera patient were sitting and taking photo and writing some query on top of
Yeah. It, like they have converted into a machine like you may have seen in the eye hospital there are some machines like
Correct,
to
correct.
place your face and so it was something like that only. The Jetson Orion was converted into that kind of device.
Okay.
Yeah. We used to take the photo of the eye. Doctor used to put the drops and
Okay.
Yeah.
The accuracy of the model was say 86%, but how good it was for true false negatives? It might have predicted false negatives too, no type 2 errors.
Correct.
So how good your model was on it?
Actually, see, I've told earlier also, there are a lot more problems in it now also. Okay, it's not like everything is working perfectly. Okay, the only thing is the negatives I haven't added to the slides. That's it.
Because in medical space, that's a major issue. False
Exactly.
negatives.
It will, if it doesn't predict well, it will act dangerous for the patients as well. Okay, so that's why we have added a human validation. Okay, this reduces the efforts of the doctors, the nurses, by for deploying these devices in clinics. But yeah, it will reduce some of the efforts. Okay, thank you. Thank you.